Having talked a bit about how the crust is deformed and how volcanoes are produced, we're going to move on now to talking about what are called the exogenic processes. The endogenic processes are the ones that take place inside the Earth. Exogenic, outside. It's where we take the land masses and we start to strip them down, rip them apart, or make them nude, denudation. We'll start off talking about weathering and mass wasting now. And then in the next module, we'll start talking more about what's called degradation and aggradation in the exogenic processes. But let's start off talking about weathering. What is weathering? Well, weathering involves all the different ways that you essentially take the bedrock, the tectonic crustal material, and you start to break it down so you can do something with it, so you can move it someplace. Physical weathering is the various ways that the natural environment breaks down rock, essentially through sort of the sheer power of the environment. Freeze-thaw of melting water and then freezing it in rock cracks and causing rock to break apart physically over time, or embedding salt into little cracks in desert climates and doing the same thing, having that salt essentially break away areas. Another form of physical weathering takes place when you have very huge, massive things like glaciers sitting on top of rocks. And then later on, the glacier melts and the rock breaks apart because it was under such great physical pressure. Chemical weathering involves things having to do with water, where chemical changes take place in the rock. This often leads to rocks over time becoming very smoothed out, turning into spheroids. It can involve water causing the expansion of minerals, or minerals changing and becoming softer, or oxidizing, rusting, or going through the process known as carbonation and solution, which is a special type of chemical weathering that takes place in limestone, where calcium carbonate literally dissolves away. Limestone dissolves, and it produces some really cool features. Here are a couple of images that show frost weathering and just the physical weathering in general of rocks, including the breaking away of rocks by glaciers over the large batholith of a half dome that we talked about a little bit last time as well. Salt weathering, causing small little niches in parts of the desert southwest. This is all physical weathering. Chemical weathering involves dissolving things over time, weakening it, causing it to rust and change and become softer. This is a limestone tombstone that is essentially melted away as a result of water slightly acidic going over the surface of the limestone and causing it to dissolve. In fact, any place where limestone is very prevalent and there's a lot of good jointing for water to get down into small little channels in the rock, you can have the creation of what are called karst landforms. You need to have good vegetation up above before the water trickles down, because that vegetation will help to produce a more acidic environment. And then you need to have plenty of space for the water to sort of move or trickle down through the ground underground, or an aeration zone. And if you do, you start to get all sorts of interesting karst landforms. And karst landforms include things like areas that you have sinkholes, where essentially the limestone is eroded away and then the ground collapses above it, or deep little karst valleys like the one shown right here, or in really extreme situations, much larger, deeper valleys, things called cockpit karst and tower karst, which I'll show you a picture of in a little bit. We often associate karst with caves and caverns, and so the map that I want to briefly take a look at right now will be back to that Mammoth Cave map that I showed you before, when I used it to talk a little bit about warping. But Mammoth Cave is all located under this northern part of the map, which is essentially a big shale cap that is on top of limestone. The limestone you can see down here, it's also underneath that shale cap with lots and lots of caves and caverns forming under that, as well as very deep karst valleys caused by that limestone collapsing underneath it. In the southern part of the map, we can see many, many sinkholes, streams that sink or disappear into the ground, into caverns. All sorts of interesting features show up here that you should take a look at as you examine this map a little bit and you learn more about karst. I thought I'd quickly show you the map of a cave. This is a cave map from central Pennsylvania where I'm from called Aitken's Cave. You can see a sinkhole on the surface has pushed down into one of these rooms like the breakdown room or the bat room or the barn room that dissolved away through all of the little cracks and fissures in the limestone that we can see here through these small little channels that the water has created. This in turn has led to the karst landscape that you see up above. And that karst landscape can be very dramatic in some situations. This is cockpit karst, very interesting limestone patterns formed in many parts of tropical areas and subtropical areas. In some areas, you can get these karst towers, which are very dramatic, as you see in many areas in Southeast Asia. And then this is a picture of karst hills in Italy, where a lot of the small towns in and around Rome are built on top of these remnants of limestone, everything else having dissolved around it. Very interesting things that chemical weathering can do. Now, once you physically weather or you chemically weather material, it breaks down into smaller and smaller pieces, and then those pieces start to move. They can be moved by water or by ice or by waves, as we'll talk about later, but often they move in large amounts through what's called mass movement. Any place where we have a steeper slope and that slope has sort of a natural angle of rest or angle of repose, what holds it together is the shear strength of all the material that's in it. Gravity is always pulling down on a slope. What keeps that slope up is all the friction of the particles that are in it, be they dirt or rock or regolith, whatever it happens to be. But through time, we have different types of processes that cause the slopes to become steeper than or more likely to movement than what the materials that are in the slopes are able to hold up. And when that happens, we get slopes failing. Slopes can fail because we're steepening it through erosion or saturating it when we have huge rainstorms. Earthquakes can also cause slope failures. Some of these slope failures are very slow and take a lot of time, like soil creep. Others of them can be very liquid and move very quickly, like mud flow. And this diagram is pretty cool because it tries to capture all the different types of slope movements. I'm just going to show you a couple pictures of some of them so you get a sense of different types of mass movement. Obviously, rocks fall when they break, rock fall. But when that collects in large amounts, we can often get scree or talus slopes, which are the collection of fallen rocks at the bottom of mountains, something that's very familiar to people who spend a lot of time hiking around parts of Alaska. A little less dramatic than rocks falling off a mountain is soil slowly creeping downhill. You can see this pathway right here has been covered by soil that has just ever so slowly crept its way down a slope. And it's not a very exciting form of mass wasting, but actually a huge amount of material in the world moves down slope as a result of the very slow movement of soil. A little bit more dramatic, but still not super dramatic, is what happens when we have permafrost areas and we get lobes of material moving down slopes, forming what are called solifluction lobes. When trees are growing on this, we often get these crazy drunken forests that are found in many parts of interior Alaska. More dramatically is slumping of materials, where large chunks of material pull and fall away. as happened in the Turnagain the Turnagain neighborhood in Anchorage during the 1964 earthquake. This is a video that shows a slow but still dramatic slump slide that occurred in Denali and is the reason why the Denali Road has been closed for such a long period of time. It's taken a lot of time. It's not as fast as a major landslide, but it's not as slow as soil creep either. We can see it developing over time. Much more dramatic are debris slides or avalanches of rock and mud. This is from the fairly recent Haynes debris slide. Here's a slide that occurred in Bird Creek near the cabin that my family owns. After a very large rain event, a steepened slope up here gave way. You can see it looking down, huge amounts of debris pushing downwards so forcefully that you can see vehicles were lifted up. So sometimes it can be very dramatic. And mud flows are the fastest, most liquid of these, and the most dangerous because they can all take place so quickly. It's worth noting that snow is a form of mass wasting as well. There are different types of avalanches, but they all are caused by the same basic thing. Snow collects over time. It goes through metamorphoses, and it starts to change. It starts to form into slabs or into chunks of ice. And eventually things get so steep, or they get so massive that they break and gravity pulls them down, and it in turn leads to different types of avalanches like the ones that are shown here, the most dangerous of which is the slab avalanche that is formed as a result of the snowpack going through dramatic changes over time, unbeknownst to the people who are often playing on these snow slopes. So if you go out and you ski or you sled or do something in the outdoors in the winter, you should know about what leads to these sorts of avalanches taking place.